Yeah, today I will talk about optimal transportation methodology for the shape reconstruction problem. And so this is ongoing work. So I'm also here to discuss with you, may have some ideas, because some part is really ongoing. So this is joint work with David Cohen-Steiner from INOIA and Simon Giraudot, PhD student at Sophia Antipolis. Part of the work was done with Julie Digne, who is now a researcher. She was a PhD student of Jean-Michel Morel, and she's now a researcher at l'IRIS in Lyon, and also with two colleagues from Caltech. So this is the outline of my talk. I will first motivate this topic. Motivation. We go quickly on the motivations, but we wish to reconstruct surfaces or shapes, like shapes also in 2D or surfaces in 3D, and from measurement data, and especially from point set data. And this point set can be hampered by defect-laden sampling. Sampling can be sparse, non-uniform, widely variable. We can have also missing data. The data themselves can be very uncertain. We can have a measurement noise, including variable noise. We can have registration noise. When we register, we need to register several data sets. And we can also have outliers. So that motivates, that calls for robustness. And this is one of the main motivations for using the optimal transportation. There is another motivation in our work. We wish to reconstruct what we call complex shapes, namely shapes with sharp features, also with non-manifold features, with boundaries. And you will see that also the initial motivation, our initial motivation was to be altogether resilient to noise, outliers, and also being feature preserving. Wanted to preserve the features during reconstruction. And if you want to preserve or recover the boundaries of a shape, it turns out that we found that we need a distance, we need a metric that is symmetric, and that's also provided by the optimal transportation metric. So just a very single slide on optimal transportation. So optimal transportation, I'm assuming that most of you are familiar with this distance. Very briefly summarized here, imagine we have a measure A and another measure B, and we wish, imagine a stack of sand. We want to move the sand from A to B. It's also why it's called the earth mover distance. And assuming we have a transport plan, namely we know how do we transport each grain of sand from A to B. And remember that here, we cannot, there are some special constraints on the transport plan. We cannot put 2 grains of sand to fill the same hole. So the transport plan must be admissible, if you want. And the transport cost, expressed with the Wasserstein 2 distance here, in that case, is simply here, this formula, where we just sum up the square distances from each atomic operation here that relocates x to y. And the optimal transport is the infimum, the minimum of this W2 distance here. So namely, the least amount of energy that takes to move this measure A to measure B. Okay, so that's the basic of optimal transport that we need here. And how does it fit in our context of shape reconstruction? You will see that we take as input a raw point set. And we will see each point as a Dirac mass. So we will see the point set as a distribution of masses, and we will try to transport it to a reconstruction or to a shape that we infer from this point set. That's the main idea behind our approach here. So our contribution is basically an algorithm that relies on this distance. So let me start by this smooth closed case. So we wish to reconstruct shapes that are smooth and closed without any boundaries. There are a number of approaches based on implicit functions, so that solve, instead of reconstructing the surface directly, they solve for a scalar function from R3 to R, defined as approximate either signed distance function to the inferred surface, or unsigned distance, or generalized distance, indicator function, or even probability density function. So there is a large zoo of functions in the literature for the implicit shape reconstruction. One assessment that we are doing is that there is very often in the literature a dilemma between, like, should we sign the data first, which is what the Poisson reconstruction method, for example, which is popular, takes as input. They take oriented points, namely points with oriented normals. Like, should we orient the data first, and then somehow life is easy? Or in the literature, we find that otherwise we need to take a more involved solver to solve for a distance function here. Here we take another approach. We sign a function. We are not going to sign the data first before solving for a function. We are going to sign a function, and we are going to sign, in fact, a robust function. So this leads to my next slide, which is about another methodology that we build upon, which is a robust distance function. So in 2011, Chazal, Cohensteiner, and Merigo, and I think Quentin Merigo is in the room somewhere, they contributed a distance function that turns out to be, that reveals to be outlier and noise robust, based on optimal transport distance between geometric measures, and based on the Wasserstein 2 distance, which is shown to be stable. I won't go into too much detail, but I will show you the formula later, but you have a defect-free point set without any noise. This is an unsigned distance function to this point set. And here, what you see here, we have outliers, a few outliers point here, and some noise. This is the robust distance function. So this function, it's an unsigned distance function that is resilient to noise, resilient to outliers, and that is shown to have many, many good properties. So this function is defined as follows. Imagine you are in the plane here. You want to evaluate that distance function at a point Q. There is a parameter in this formula, which is m, namely the mass. So we grow a ball until it encloses this mass m. And then we measure how much it costs to transport this mass to the query point. And this is given by this formula here. And this is shown to have many good properties. It comes with theoretical proofs. But there is a parameter m, which is this mass. This must be user-specified, like the scale, if you want, that allows us to tune the resilience to noise and outliers. That also very often depends on the point set properties, and that is global, not noise adaptive. This is a first contribution that we did this year, recently. We wanted to make this function noise adaptive, namely adapted to the local node level of noise. So this is an extreme example I've chosen here. This is a point set sampling a circle with a variable noise, like a lot of noise here, noise free here. If I depict that function along this slice here, the red line, I have a function like that. If I choose a scale, here the scale, I call it k, because this is basically for a point set, the k nearest neighbors that we select. If I choose a small scale, you will see that on the noisy area, I have a noisy function here. But I will be faithful here. Here, I will have a faithful local minimum here. If I choose a large scale, I will be smooth indeed here, but you see that this has shifted to the right. So I'm not able to locate as accurately the function. I will be overly smooth here, but I will be fine over here. So what we did is the following. We first considered a case of an ambient noise. And we assume we have a uniform measure, namely a discrete distribution of masses in space, in d-dimensional space here. So if you have the query point Q here, this is the ball that encloses a mass m. This square distance here is proportional to a constant times m to the power d over d, 2 over d. So that's proportional. D is itself proportional to m to the power 1 over d for q fixed. And this function, what we, if we consider now, if we divide this function by m over to the power alpha, this function is decreasing for alpha greater than 1 over d. Okay, we are going to simply divide this function by m over alpha and observe that it decreases for certain condition over alpha here. Remember, our goal will be to tune the m automatically here. This is in the case where, if you want, we are at the scale of the noise. We are within the noise. Okay, so that's this is like a uniform measure around us. If now we have a larger scale, and imagine we are sampling like a surface, imagine now we have a uniform measure on a K submanifold here. If it's a submanifold like that here, we will have, here I take this example, we have this time the square distance that's proportional to C constant times m over 2 over k plus L square, therefore proportional to m to the power 1 over k for q fixed. And this time, if we divide by m over to the power alpha, this will be increasing for alpha lower than 1 over k. Okay, so what is it useful for? What we do intuitively, if you want, we wish to find the smallest scale for which the apparent dimension has the right dimension. Okay, so imagine here you are in the plane here. We have some noise, we have sampling a curve, and the scale is m, 10 nearest neighbor, let's say small scale. The apparent dimension will be 2 here. And that's like an ambient noise in 2D. And now we are in this case. So this function is decreasing for alpha greater than 1 over 2 here. Now, if I take a large scale, you see that the apparent dimension here is 1. So we are going to observe how does this function behaves, if you want, according to m that we will vary. And in that case, we perceive that's an apparent dimension, a 1 submanifold in 2D, and this function is increasing this time for alpha lower than 1. So this is enough for us to devise a function, simply. We assume we have a single assumption. We want to perform, to devise an algorithm or a distance function that is noise adaptive and that relies only on a simple assumption, which is that we look for a submanifold of known dimension. For K submanifold in D-dimensional space, we devise this formula. This distance is simply the infimum of D to the divided by m to the power alpha, with alpha between 1 over d and 1 over k. Okay, so we are cooking, if you want, we are cooking a new formula that has a property that we seek. Basically, we seek for the m as small as possible to not oversmooth, but large enough to perceive the right apparent dimension here. So for a surface in 3D, we select alpha equal 5 to 12 to satisfy this condition here. 1 over d and 1 over k here. So now, when we do that, so we evaluate for a wide range of m, and always, at any point in space, we pick this infimum. And now, for a variable noise like that, we have that the function is like this, very accurate over here for the noise-free case, and this time has a right scale. You see that the scale suddenly goes up here to perceive the right dimension here. Okay, so it's like a distance function that is provably robust, provably resilient to outliers and noise, and we make it noise adaptive. So what are the properties of this function without going into the details? So this function is shown to be, again, robust and one semi-concave, has the right robustness properties that were expressed in this paper here. And we need, but we need to take a minimal M0 properties for the range of M. Huh? We need to do that. And this is, in this paper, proven to have the correct topological inference that we recover the right topology for under certain conditions here. So quickly, just one result here. This is a point set with a variable noise. This is, if you want to be resilient to noise over here, if you use the Poisson reconstruction with a large scale, let's say, with a coarse scale, you will over-smooth everything. If you choose something in between, you will see some defects over here. You will capture that fine. And if you select a too fine scale, you will be not noise adaptive, so you'll have many defects in the reconstruction here. And we obtain something that ranges between something faithful to the point set and noise adaptive over here. Okay, so this, I won't go into more details for this approach. This was published at the last Eurographics Symposium on Geometry Processing. And once we worked on this approach, making these methods resilient to noise, resilient to outliers, to variable noise, the other question was, how can we now reconstruct a shape that is piecewise smooth with boundaries? And we are again using optimal transportation metric, but in a way that is completely different. So the way we use it, so if you look in the literature or what can be found in the previous work, there are many work that try to aim at being resilient to the defects in the sampling that I've listed before. I try to put a dot every time these approaches are resilient to a certain type of defects. Here, sampling defects, sampling resilient to noise, to outliers, feature preserving, boundary preserving. So what was our assessment is that it was very hard to find an approach that can put a dot in each of these columns here, to be altogether feature preserving, including boundary preserving, and resilient to noise and outliers. The approach I mentioned before, where we are assigning a robust distance function, for example, is only suited to closed and smooth shapes. So turns out we could not really adapt it to be feature preserving. So we had to choose another methodology. Our approach is completely different, still relying on distance between measures. So this time, we see the point set again as a discrete measure, distribution of masses. This time, we wish to find a triangulation T such that S, the point set, is well approximated by uniform measures on the 0 and 1 simplices of T. So in 2D, that means that we have a measure, so a distribution of masses, and we want to approximate that measure by another measure, this time continuous, whose support are the edges and vertices of that triangulation. Okay? So that's not just an optimal transportation problem. That's called the optimal location problem, because we also seek for the triangulation. We are not given the target measure, if you want. We also need to define it. Now the question is, of course, how do we measure the distance between this discrete measure and the continuous measure of the triangulation? The answer is optimal transport between measures. That's, I think, the right tool that we need. This is really perfectly suited to this problem. And now, how do we construct a triangulation that minimizes this distance? For that, we don't have yet a clear answer how to do that. And in the first proposal, we simply, because that's the optimal location problem, for the moment, we devised a first algorithm that proceeds by greedy decimation of a triangulation, but where each decimation operation is driven by optimal transport. So in our setting, we have a measure A, discrete measure, that we transport to a continuous measure. And this measure is constrained to be piecewise continuous or piecewise uniform on edges. So we are going to add some constraints on this target measure in order to be able to solve for it. So now, imagine an even simpler setup. Imagine I know the transport plan. I'm given a transport plan. I know where each point goes to. And also, I assume that the transport plan is binary. Namely, I transport a point set entirely to either an edge or to a vertex of the triangulation. For the moment, I'm not allowed to split the masses into submasses. If we do that, then if we know we have a set of masses that transport to a vertex, the formula is trivially this formula, sum of mass mi, which is, let's say, the mass of a sample Si here, a pi here, and times square distance from the vertex to this thing, to this sample here. Okay, trivial formula if you know the binary transport plan to transport two vertices. Now, if you know where these samples, this point sample transport to which edge, I depict here variable radius depending on the mass. They can have a variable mass. If you know where they transport to an edge, in 2D, there is a closed form formula. It's enough to sort the point along the edge. If you parameterize the edge, you allocate bins that are larger when you have a larger mass, and there is a closed form formula over here. Okay? It's trivial. It's just if we know the binary transport plan, there is a closed form formula on the edge of the triangulation. Here we transport, so the points are embedded in 2D, but we transport this point on an edge of the triangulation. Yeah. So it's indeed a sort along the edge. So when we are using such binary transport plan, in fact, we do things a little bit different. So what we do, we simply project each sample to this nearest edge of the triangulation. But so imagine all these samples here, we transport them to the nearest edge here. But if we measure with a closed form formula that it is cheaper to transport these samples to the end vertices of that edge, then we call that edge a ghost edge of the triangulation, and we transport them to the end vertices. And this is that's a point set on a hand drawing of a horse. And imagine I am given a triangulation here, and you obtain something like that, where the edges of the triangulation that are traversing here, where there are no point set, you see that for these edges, all these samples are classified, are transported to the end vertices of that edge. That is highly suboptimal, but we have a closed form formula. And that's a simple setup for the moment. It's a warm-up, let's say, for this approach. So the total cost comes here. Now, how do we proceed? How do we make an algorithm out of that? Simply, we put all the point set, the whole point set into as vertices of a Delaunay triangulation. So we have a canonical triangulation here. And then we decimate the triangulation where each decimation operator through edge collapses, what we saw yesterday, I think, in 2D. We collapse edges using a modifiable priority queue where the sorting of that queue is performed through optimal transport. So that looks like that. This is a point set inserted into a subset of the point set inserted into the triangulation. I depict the transport cost here. When we decimate, we have also edge flips that happen to make sure that all edges can be made collapsible in the queue. And we can prove that all edges can be made collapsible while preserving a valid embedding of the triangulation through a sufficient number of flips. And when we decimate, you see what happens is that the edges of the triangulation become the support of that measure. You see that these samples are transported to the edges or to the end vertices, and we obtain a reconstruction like that. Because this error metric is symmetric, we preserve the boundaries. And now, simply, the triangulation is the support of the reconstruction. It's also the support of a scale space approach. We traverse the scales here, so the edges become longer and longer. That also, automatically, we have also an even more robust approach through this scale traversal on the triangulation. So how does it work? The answer is, in a noise-free case, it's not any better than another reconstruction approach, but in a noisy case, then it is extremely stable. This is a canonical example where we have sharp features, boundaries here, noise-free. When we add a little bit of noise, still resilient, outliers, even more noise, but here we even have a hard time drawing what's happening here. So we have something like that. And when we add even more outliers and noise, it turns out that it's really, really stable. So of course, it starts degrading at some point, but gracefully, if you want. And that's exactly the property that we seek, that we are after. We are after a method that is resilient. What's interesting also is that when you have a lot of noise here, where in the middle you can hardly distinguish what's happening, the algorithm transits through a state where it's very messy in the middle, but because of the scale space, we see these edges are long. They rely on this part to recover the feature in the middle here. That's also a feature that we are looking for reconstruction of large-scale urban scenes where the laser scanners in general measure nothing on the sharp creases of the buildings, and we need the walls to reconstruct these features. We can also add, say that each point has a variable mass. Here I've taken this image and I wanted to vectorize this image. And it turns out that we have something like that in the end, where this time the closed form still works for a variable mass, of course. And that turns out to be an interesting alternative to current image vectorizers also. So the limitation of this approach is that we have a binary transport plan, remember. So it's very simplistic, very basic. The problem is that you see these edges are traversing edges. Because we project these samples to the nearest edge, well, they will be, if you were not transported to that long red edge here, with a red transport plan, they will be removed from this target of the edge, and therefore that will induce a tangential transport plan on the edge, because we force a uniform measure on the edge in our formula. So, of course, what we tried next was to use a fractional transport plan, where we allow this time to split the masses into submasses. And turns out that was absolutely required for moving to the reconstruction of surfaces this time. Absolutely necessary. I don't tell you all the details, all the justification, it's written in the paper, but we really need that for surfaces. So we wanted something like that. So that's a small, again, canonical example of a noisy staircase. Wanted to be binary preserving, feature preserving, resilient to noise, and also, why not, reconstruct and simplify altogether. So we wanted to end up with also something that is what I call effective at approximating the shape, namely a good complexity between distortion and description length of this mesh here. Namely, which I can measure how many faces or vertices for which distortion. So I want always to have a good trade-off between the two. And even better, I would also like to find automatically that scale. I would like to stop, for example, when I reach 2 faces here per step of that stairs. So for surfaces, I would accelerate a little bit. For surfaces, it turned out we needed a fractional transport plan. So this time, slightly more complicated. For each sample, for each point Pi, we allow it to be split into submasses. We have a mass Mi, and we split the mass and can transport it either to the faces of a triangulation embedded in R3 this time. And we had also, there is no closed form anymore. No closed form anymore. So we needed to discretize the problem, and the way to minimize this error due to the discretization is to compute a so-called centroidal Voronoi diagram on the faces of the triangulation. It looks like that. It's a Voronoi diagram where each generator of the diagram coincides with its center of mass. So we compute a centroidal Voronoi diagram like that. Each of these cells is seen as a bean. It can receive mass. On the edge of the triangulation, each edge of the triangulation can also receive mass. Each vertex of the triangulation also can receive mass. Okay? And the additional constraint we will add, we will say that the measure on the triangulation has to be piecewise uniform. Namely, we will compute first the capacities of this mass, of these beans, here the area of each bean, and we will say that they can receive mass from anywhere, but the measure on that entire triangle has to be uniform. Same along an edge, and at a vertex we can receive anything. Okay? It's a pointwise bean, if you want. So you see the idea is that the triangulation is the support of a piecewise uniform measure, and the 0, 1, and 2 simplices can receive mass. This is the main concept. How do we solve for that? The answer is very simple. It's linear programming. We can say that we wish to minimize the sum of Mij, G being the target bean, I being the Mi here. So Mij is a fraction of the mass that leaves from Pi to the bean J. We minimize the sum of mij times square distances between pi and bj, bj being the target location, the center of mass of that beam. We can also write a closed form here, by the way. We can also write a closed form for a beam, but not for the entire triangle. And we have some constraint. We need to solve. That's a linear program. We need to solve only for these variables, mij's. Those are not variables. And the constraint are the mass conservation. We wish to have that the sum of mij equal mi. That this measure is uniform on each edge or face. This is a piecewise uniform constraint. And of course, positive densities. Okay, so that's a linear program. We use a coin law or a linear program solver for that. So it looks like that. So each sample can be transported to either an edge, a face, or a vertex locally. What is also interesting with this framework, so it's very, very slow. So we are currently working on accelerating this problem. We tried several tricks to accelerate it, but I'm glad to hear some ideas from you to accelerate that. What is interesting now is that we can do an expectation maximization framework. We can relax this algorithm. Namely, we can, for a fixed, imagine this is my point set. I have a single triangle here. I solve for the transport plan. You see, that's the transport plan. Who is transported to whom? But now I know the transport plan, so I can freeze it and relocate the vertices of the triangulation so as to minimize the transport cost. If I do that, I will relocate here, and therefore I can recompute the transport plan. If I do that, you see that this triangle lines up to the data. And this is what also we wanted, especially for urban scenes. We want to have that the polygons line up to the windows or to the sharp creases and things like that. Okay, so that's an EM framework where we freeze the transport plan, update transport cost, and so on. This is true because we know the barycentric coordinate of the beam centers. Therefore, we can relate them to the vertices. So the degrees of freedom of this relocation algorithm are the vertices of the triangulation. And for free, we have also a dimension detection thing. Because remember, we transport either to edges or to faces. You see here, when I solve, the solver finds that they transport only to the edges. So therefore, when I do that, I have somehow a dimension detection thing. Intuitively, if I have a tree in my scene, in an urban scene, the trees will be reconstructed as a set of edges, not faces. This is also what I want. Now the question is, when should we stop? When should we stop this algorithm? Because remember, I was using a greedy algorithm that was decimating the edges of the triangulation, one after the other. I can always decimate as long as our edge is collapsible. When should we stop? That's again a scale detection problem. That's again an automatic scale detection problem. So this is ongoing work. I'm also glad to discuss with you during this week about that. I don't have a definite answer. But what we are currently experimenting is the following. We say that a good simplex, a good face or a good edge, is an edge that has a large measure, so that covers a large area, for example, for my domain. Why? Because the total area of my domain, let's say of a building, that's a constant. So if I can maximize the area of a simplex, I need fewer simplexes. I will be effective. Receive a high mass covers a large measure. You could say that's a bit redundant here, but has a small transport cost. So a very good simplex, if you want, receive a lot of mass, covers a large area for a small transport cost. So there is a trade-off like that. What we do during decimation, we monitor this quantity. I don't give you the formula here because we have a little variance for the moment. It's a trade-off. It turns out it's an average mass per beam that works very nicely divided by this transport cost. And when we monitor this during decimation, it turns out we have peaks of this quantity, this average global quantity. And for example, for the staircase, we stop indeed when we have 2 triangles per step. So how does it work? This is a picture I've taken from our first implementation. So this is not super easy to implement thing because there is a linear program, there is a 3D triangulation. we force each edge to be collapsible with a valid embedding that requires solving for the polyhedron kernel in 3D, again, linear programming, and so on, modifiable periodic Q, few things like that. But our first implementation gave something like that. We insert these points to a 3D Delaunay triangulation. I depict here the measure, the density provided by the solver after solving. I depict here the transport plan. These green segments are the transport plans. And we start decimating. We decimate, 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 and decimate more. But every time we collapse an edge, we relocate the vertices in the neighborhood using this EM framework I mentioned to you. Okay, so the first time we run this algorithm, we obtain exactly that. Where these vertices or the edges lined up with the boundaries, that we had the sharp creases, and so on. Still not exactly perfect. You see, maybe you have good eyes, you can see that there are 4 faces covering this step here. This is something we cannot get rid of easily, only through edge collapse operators. This is a transport plan. So when we compare this to, let's say, the Poisson reconstruction algorithm, in cases that are difficult, namely where you have a sparse sampling with sharp creases here, this is when we use an implicit function, was really fragmented for the sharp feature. We obtain something decent for this sharp crease here. And this is an example, a small excerpt of LIDAR data on an urban scene, and we obtain something like that. We are not scaling at all, I warn you. This, for a little house, this takes 20 minutes, and it's impossible to run this algorithm on a large urban scene at the moment. So this was published in this journal of mathematical imaging and vision last year. So as a summary, we have a focus on robustness. This was really our initial motivation. We wanted to be resilient to noise, including to variable noise. For the smooth closed case, we have something. For this piecewise smooth case, it's more difficult to assess that for the moment. Wanted to be resilient to outliers, all together while being feature preserving. What I showed you, the last algorithm, is a greedy algorithm. It's fine to coarse. We also tried coarse to fine, of course. This is still ongoing work. Our main issue with this algorithm is that when we decimate here, we also want to have another guarantee for this algorithm, is that with a valid embedding. We want that this surface, these faces do not self-intersect. And if we force that property, it turns out that we are not able to prove that using a sufficient number of flips, all edges can be made collapsible in the periodic queue. So that's currently an issue with this algorithm, that when we are, especially at coarse scales with very skinny triangles, almost none of the edges are collapsible. So this periodic queue becomes very, very sparse, and that's currently something, either we have to change the data structure, or we have to devise something that provide the same constructive guarantees. That's currently ongoing work. So our next step is to work at the scale of entire urban scenes. So that's some work that I'm currently working on with Florent Lafarge. And we also want to go beyond reconstruction of surfaces. We want to go toward consolidation of surfaces of urban scene. Consolidation means enforcing some canonical geometric relationships like orthogonality, coplanarity, being resilient to missing data also. This is really beyond reconstruction. This is something we are currently working on. And we start really working at the scale of urban scenes. So this is a piece of Marseille, where you see this is a point set and those are the buildings. So this is a construction performed by Florent Lafarge on this scene. We are also working at the scale of entire scenes. So, and that's part of this work was partly funded by this ERC starting grant IRON on robust geometry processing. Thank you very much.
Okay, thanks. Well, thank you for the very nice talk. First, I have a comment. You haven't pronounced the term curvature during your talk. And however, you spoke a lot about optimal transport. So I guess that curvature is present somewhere. And I would like to know if you can precise where exactly, and if you can comment on the influence of curvature on what you're doing.
That's right, yes. I have not pronounced the term curvature. Although we want to be feature preserving, and obviously a feature is what? A discontinuity where there is a singularity in terms of curvature. So to tell the truth, in this work, we explicitly wanted to stay away from estimating the curvature. So we have alternative approaches where we aim at detecting the features through curvature estimators. From our experiments, we found that very often we again need to tune to select a scale to detect the feature. Here, if you want, what we hope is that there is some curvature in the reconstruction, indeed, in the end, the features and so on, including the boundaries, which can be seen as a special type of curvature also. But we want it to emerge as a distance minimization thing. So we never wanted to estimate the curvature here because it's too much scale dependent. Although we also know a little bit more how to select the scale automatically. But now in this, we are currently thinking, we never succeeded in finding to reverse engineer, let's say, the transport plan to, for example, deduce or to have, through the transport plan, a curvature estimate here. But I'm guessing this should be possible. I'm guessing by analyzing, let's say, the tangential component of the transport plan versus the normal component, there must be a way to relate the transport plan of our framework to the curvature of the inferred shape. I'm guessing that, but we have not succeeded in doing that until now.
Again.
Thank you very much.
Yeah, so, beginning,